This example comes out of 6.1, reciprocal quotient and Pythagorean identities. The first thing we're asked to do is consider this equation, cosecant theta equals cotangent theta over cosine theta. We might ask ourselves right away, is this an identity or is it just an equation? So the first thing that they ask us to do in this example, and they will ask you to do in the 6.1 questions, is use your technology, your graphing calculator, to decide whether this equation could be an identity or not. Now, remembering what we did in a previous example, if we graph each side of this equation, now to graph cosecant we need to graph 1 over sine x. And in my other side I need to graph cotangent over cos, which means 1 over tan divided by cosine. And graph these two things, and what you'll see is that it basically draws one graph on top of the other. You'll see some asymptotes at 0, pi, 2 pi, negative pi, negative 2 pi, and I suppose the question said degrees, so we could have left this as negative 360 degrees, positive 360 degrees. And you'll basically see a strange curve that goes up, and then it goes down. It goes up, and it goes down. And it keeps alternating like this for as long as you want to draw it. So from negative 360 to positive 360. The fact is, when you draw y1 or y2, they draw the same curve. So you could definitely decide that graphically it sure looks like it's an identity. You're not getting two separate graphs that are intersecting each other. You're getting one graph drawn twice by two different sides of the equation. The next thing we're asked to do is numerically verify that the equation is true for some angle that's given to us. It might have been an angle in radians or an angle in degrees. In this case, theta equals 45 degrees. If I remind myself what I know about 45 degrees, at 45 degrees the coordinates on the unit circle are 1 over root 2, 1 over root 2. So cosine is equal to that, sine is equal to that. So if I set up a way of verifying this thing, I might set up a little left side, right side table and say the left side of this equation is cosecant theta, which is 1 over sine theta, which if I let theta equal 45 degrees, I have the reciprocal of sine is going to be root 2 over 1. So sine of 45 degrees, 1 over sine of 45 degrees. On the other side of this thing, I had cotangent theta over cosine theta. So I need to say, what's cotangent 45 degrees over cosine of 45 degrees? Now, if you figure out what tan of 45 degrees is, you discover that it's 1. So cotangent is also 1. Cosine is 1 over root 2. And if I do 1 times root 2 over 1, I get an answer of root 2. The left side and the right side are giving me the same answer, which means at the very least for theta equals 45 degrees, this equation holds true. The last thing we're asked to do with this equation is to determine non-permissible values in degrees. Non-permissible values, if you remember from previous courses and earlier in this course, stem from you having anything being divided by 0. We can't divide by 0. So look at any denominator that you have in this equation, in this identity, and see if any of them can equal 0, or don't let any of them equal 0. So if I look, even in this last example where I did the left side, right side table, I do have some denominators. I have a denominator of sine theta, so I can't let that equal 0. I also have a denominator of cosine theta that I don't want to let equal 0. So I do need to remember, where does sine theta equal 0? 0, pi, 2 pi, or 0, 180. So theta can't equal 0, 180 degrees, 360 degrees, etc. And where does cosine equal 0? Well, at 90, 270, etc. So theta can't equal 90, 270, and any 180 past that, 450, etc. If you look at all of these non-permissible values, they would go on indefinitely. You could list a million of them if you needed to, but the fastest and best way to do this would be to say, what can theta not equal? 0, 90, 180, 270, 360, any multiple of 90 degrees. So if you said 90 degrees times n, when is any integer, you would have listed all the non-permissible values for this particular identity.